To illustrate a trunk port, basically, we talked about the possibility of having a switch or a hub. Now, this is a switch. When you see these four arrows or these two sets of arrows with four heads, this designates a switch. This over here designates a router. Now, normally in the case of a hub, when you connect all the machines to a hub, every PC belongs to the same network. On a switch, you have a choice that they could belong to the same network, or you could create multiple networks, what is called virtual LANs or VLANs for short. The LAN, the word LAN stands for local area network, and the V in there stands for the word virtual. So technically, you can take a 24-port switch and break it down into multiple networks. You could break it down into two networks, or leave it as a single network, or even break it down into three networks, four networks, whatever, depending on your needs, right? So here we see a switch which has been broken down into one virtual LAN here, VLAN 1, and another virtual LAN, VLAN 2. So technically, we have two virtual LANs in here. If you have two VLANs or virtual LANs in here, the addressing scheme for each of these VLANs will have to be different, right? One is, for example, 192.168.1.x/24, meaning to say the first three octets are considered the network address, and the last octet here will be the host address, the device address. For VLAN 2, we have 192.168.2. You understand that this network address is a /24. That means the first three octets are most relevant. And you see that the first three octets are different in each case to designate a different VLAN. If you are on the same VLAN, then the first three octets will have to be the same if it is a /24. So here we have a situation in which we have two VLANs. Now, technically, if you have two VLANs, you could have two ports, one from each VLAN being connected to the router. So technically, you could have one port from VLAN 1 and one port from VLAN 2 connected to the router. The only problem with that approach is that it's going to use up two very valuable, very expensive ports on the router. So technically, and sometimes beyond that, you could have the possibility that you have three VLANs or four VLANs, right? So that could be possible as well. So this way, this would once again require even more ports if you have three or four VLANs. In any case, the idea here is you want to minimize the amount of ports you use on the router. So the way to do this is to create a trunk port. The idea behind the trunk port is to be able to transport information from multiple VLANs, right? So basically what happens when the packet leaves the switch, right? It will be tagged with the VLAN number, whether it belongs to VLAN 1 or VLAN 2. And then the router will understand where this packet is coming from and be able to route accordingly. So that's the idea of the trunk port, being able to send information from multiple VLANs and exchange information from multiple VLANs. So technically, if you look at any switch, what you will see that you can configure a switch to be an access port, which is kind of the default configuration. And by default, all ports will belong to VLAN 1. That's by default. There'll be access port in nature, and they will all belong to VLAN 1. However, you have the ability to configure some of the access ports to belong to a different VLAN. So here we show you the same configuration we were discussing, in which ports 1 to 12 belong to VLAN 1, and ports 13 to 23 belonging to VLAN 2. And we're going to use the last port, port 24, as a trunk port, which will carry information from both the VLANs. So now you can see that the last port is not an access port. It has been configured as a trunk port. So basically, there are two possibilities here. You can configure a port as an access port, which is the default setting, and you can configure a port as a trunk port and designate the VLANs that it will carry information for. So in here, this port, this is a single port on the router, will have what is called two sub interfaces. There'll be only port one here. You can see port one in both cases, but there is a sub interface reflecting the VLAN number. So port 1.1, meaning to say this is going to carry information for the first VLAN, and this is designated its own IP address, which is 192.168.1. So you notice that the address here, 192.168.1, is reflective of the network address for that VLAN 1. Then we have another port, which is 1.2. So basically same port, but is sub-interface 2, which is VLAN 2, has the address 192.168.2 to designate that this belongs to VLAN 2, 250. And basically, most companies tend to use either .1 or .254 as their router address. So this is the address you're going to configure on your machines as the default gateway. The default gateway is an IP address that reflects the address of the router. So this is where the computer will send information to, which is the default gateway, if the destination IP address is not on the same network. If it feels a packet needs to be sent to something outside the network, it will send it to the default gateway. So basically the router will get this information and send it or route it to any possible destination that you have in mind, including the internet. So hopefully that will covers the explanation for the trunk port. We'll talk more about the trunk port as we go along. And we'll talk obviously more about that in the Cisco course, which will come after this course, hopefully, as well. So there's quite a few courses I have in mind, including the Azure as well as AWS courses, and that we'll be discussing here. Now let's talk about the link aggregation control protocol. This is also an interesting one. The link aggregation control protocol, usually abbreviated as LACP, is basically a combination of ports that you can aggregate together to increase speed or give you some redundancy. So many a time, if you have, let's say, two 24-port switches in here, instead of using only one port to link the two switches, many companies would possibly use two ports to connect together and basically configure what is called LACP between them. So meaning to say those two ports, so those two connections will be responsible for taking traffic from one to the other and vice versa. So this is traffic flow actually in both directions. And then what happens is that if one of them goes down, everything will still continue to function because they are kind of joined as a pair, right? If one goes down, everything will continue to function. If both are alive, then traffic will go on both those ports or both those links to expand the capacity. So in theory, what we are doing by aggregating multiple ports and using multiple cables is we are increasing the throughput of this connection, right? So instead of, let's say this was 1 gig each, this would become now 2 gig connection, right? You could go up to 4 ports and connect 4 ports together in an LACP configuration, which will give you even 4 gig connection, right? Which is 4 gigs, so 1 times 4, right? Which will give you 4 gigabit per second throughput. If it's a 10 gig port, even better, then you'll get up to 40 gig connection between the two, right? So that's the idea behind the LACP protocol. So there are 2 other topologies we have to discuss. We already discussed the mesh topology before, and we talked about the star topology. The other 2 topologies we need to discuss is the bus topology and the ring topology. In the bus topology is also a multi-point connection in here, where we basically have a cable that goes across, but it will have basically T connectors at certain points in there. The T connectors allow you to add a different node or additional node to this line in here, right? This was the first way that Ethernet, basically 10 base T, was set up. The 10 base T, the 10 megabits per second, you could set it up in this format using a bus topology. And actually, I have done this way back in 1995, 96. That's how old this technology is. So this is some like 30 years ago, in which I had set up this type of topology, right? So in which you have, once again, as I mentioned, T connectors over here, and then you add a coax cable. So this is actually a coax cable, and there are T connectors in here, which connect all the coax cables together, and you can add computers as you move along. And then you need terminators. So this is an endpoint. At the very endpoint, you have to make sure you have terminators, otherwise the signal keeps on bouncing back and forth, and the signal does not actually work properly. So there's, at the endpoint, you have an end connector that you basically put in place to close the possibility of signal bouncing. So there are two terminators at the very end. So the bus topology, as I mentioned, was one of the first topologies used in the design for early LANs, or early local area networks. The nodes are connected to the bus by drop lines and taps, right? A drop line is a connection running between the device and the main cable. And the tap is the T connector. As I mentioned, it is a T. Literally, it looks like a T to connect the coax cables together. As the signal travels along the backbone, it attenuates, right? Becomes weaker, right? So you can imagine, as I mentioned, there's a limit, about 8 to 10 machines in real life is what I came across, that it starts to slow down quite a bit. It becomes weaker as it travels along. Therefore, there's a limit of the number of taps a bus can support on the distance between those taps, right? So one issue is the distance itself. Second is because it is half duplex, only one machine can send, the other one would have to receive. All the other ones are listening into the conversation. That's how hubs normally work. And in this particular case, there's no hub in here, but the bus topology works in the same manner. Okay, so the advantage of the bus topology was it was easy to install, required less cabling than a mesh or a star topology that we had discussed before. Therefore, there is a limit basically on the number of taps a bus can support on the distance between those taps. So basically the distance was one of the limitations. And the fact that this was half duplex, of course, that became a disadvantage as well. As the signal travels along the backbone, it attenuates and becomes weaker. Therefore, there's a limit on the number of taps a bus can support and on the distance. One cut in the wire brings down the whole network. The other topology, which is no longer in use, is the token ring. So in a ring topology, each device had a dedicated point-to-point connection with only the two devices on either side of it. A signal is passed along the ring in one direction from device to device until it reaches its destination. In this case, each device in the ring incorporates a repeater. And when a device receives a signal intended for another device, the repeater regenerates the bits and passes them, resulting in strong signals. So the advantage of the ring topology was a ring is relatively easy to install and reconfigure. Each device is linked only to its immediate neighbors. And the only constraints are media and traffic considerations, the maximum ring length and the number of devices. Fault isolation is simplified. If one device does not receive a signal within a specified period, it issues an alarm. The alarm alerts the network operator to the problem and its location, which was great that it had an inbuilt feature for fault isolation. The disadvantage of the ring topology was a break in the ring, such as a disabled station, can also disable the entire network because you're depending on that station to be working and being used as a repeater.